All right, let me see if I can turn on the camera here. So Chris's might be scary here. Let's see. I think it's, what is it? It's Control Apple 2. Here we go. We're going to try it. I think you can see me. Okay. The first thing is binding energy. And the good news is that if you learn how to do binding energy problems, almost every single problem on this test uses the same technique. Okay. And the concept here is that if we've got a bound helium-4 atom, right? If we tear that apart into two free hydrogen atoms, that is, we represent it this way, right? And two neutrons, these things have more mass, and this has less mass, right? Now, so in chemistry class, you learned that the mass is conserved, right? And now in physics class, you're learning that mass and energy are conserved here, right? And the reason this has more mass is that we did work. Okay, we did work to separate these things. We had to put in energy, and that energy has mass. E equals mc squared, right? So the mass of a certain amount of energy is just E divided by c squared. Now, c squared is a big number, but it's not infinity, right? This is a profound thing, right? If you throw a baseball, that moving baseball has more mass than the baseball had when it was sitting still. If you lift a mass up, if I take something and I lift it, okay, it has more mass when it's higher than it does when it's lower. So this is just a crazy thing. Now, remember, this denominator here, right, is 3 times 10 to the 8th squared. So that's 9 times 10 to the 16th. So we can't really measure this with a balance or something like that. But in the case of the strong nuclear force, there's a noticeable difference. We can look this up on the table and get a difference in mass. Okay. So understand that binding energy, the more work you have to do to separate it, the more stable it is. So the bigger the binding energy, right, that's really stability. It's sort of a weird backwards thing, right? The bigger the binding energy, especially per nucleon that you have, the more stable it is, okay? And I know you've already seen this video, but if you didn't watch the video, I think it's like 30 or something like that, right? If you didn't watch that video, why don't you go back and watch it? It's probably the most important thing, is that if we talk about binding energy per nucleon, right? This is the highest binding energy we have. So this graph here, this is our atomic mass number, right? And then this axis here is binding energy divided by A, right? Binding energy, we call it BEPN. Binding energy per nucleon. This is a measure of the stability. So this is the most stable right there, right? Notice that if we start out here, this is like where uranium-235 is, right? Something right there. Notice that if we split uranium into two nuclei that are maybe, half that, right? We release a certain amount of energy, right? If we go from here to here, we're going to more stable. When you go to more stable, you're releasing energy. Okay, so this is a fission reaction, right? But look at this. What if we can join these together in a fusion reaction? We can fuse them together. Well, boy, that's a whole lot more energy, right? Fusion can release that much energy, right? So this is, the premise behind the H-bomb, to put things in kind of a grim perspective, right? This fission reaction here, a uranium bomb, that's what we dropped on Hiroshima and Nagasaki in World War II. But anyway, so this is just crucial, and you're going to see this graph on IB tests. I'm also going to post some videos because there's a way to find Q value for it based on binding energy per nucleon. It's a slightly different calculation, but I've seen it a couple times on the IB test, so I'll post those. That'll be like a new thing, but look for that on the classroom.